Hello and welcome. Today we're going to be looking at solving equations with radicals. Some things to point out here at first. When we're using the power rule for solving an equation with radicals, if both sides of an equation are raised to the same power, then all solutions of the original equation are also solutions of the new equation. However, it's important that we note that when the power rule is used to solve an equation, every solution of the new equation must be checked in the original, because it is possible that you can create extraneous solutions. So make sure we keep an eye out for that. We'll be talking about that as we go through and solve these equations that we have to do today. So here's a set of steps for solving an equation with radicals. First of all, we want to isolate that radical. So again, get one radical term alone on one side of the equation. Then we apply the power rule, so we raise both sides of the equation to a power that is the same as the index for the radical, and then we solve the resulting equation. If it does still have a radical, then we'll go back to step 1 and go through step 1 and 2 again, and at the end again just making sure we check all solutions in the original equation. So looking at this first example, we've got a square root of 3x plus 4. So remember, when we use that terminology of the index, we're talking about the 2 there for that square root that we don't actually draw. So this one already has step 1 done. The radical is isolated. And again, I just put that 2 in there to emphasize that it's a square root. So we apply our power rule. So we'll take both sides of the equation and square both sides of the equation. So on the left side, that will just leave us with the 3x plus 4. On the right side, we square 8, we get 64. From here, we just solve this equation. We're on to step 3. So we would subtract the 4 from both sides, and we get 3x equals 60. So we'll divide both sides by 3, and we get x equals 20. Now, it's always a good idea to check your answers. In this particular case, though, we cannot have created an extraneous solution, so let me explain a little bit about that. The possible time where we would have created an extraneous solution would have been here, where we squared both sides of the equation. Once you've done a few of these, though, you realize that the only time you create an extraneous solution is if you square a negative number on either side here. So we squared that square root, which can't be negative, and we squared 8, which is positive, so we can't have created an extraneous solution. Again, still a good idea to check your answer. If you want to pause and do that, go ahead. Here are a couple more examples for us to try. So example 2, very first thing we need to do would be to subtract that 3 from both sides of the equation, because we need to isolate that radical before we apply the power rule. And so we get the square root of 5q minus 1 equals negative 3. So at this point we would apply the power rule. If you notice, however, we just squared a negative 3. So we actually just created an extraneous solution. Now we could finish solving this, but again, knowing how these work out, I know that this will not actually give us an actual solution to the original. So next we would add the 1 to both sides, and so we'd end up with 5q equals 10, divide by the 5, and we get q equals 2. Again, we could plug that back into the original. We'd end up getting the square root of 9 plus 3 equals 0, which does not work out and ends up being 3 plus 3 equals 0, which is 6. So again, this would be an extraneous solution. At this point, if you can look at this first step and see that there's going to be no solution, I'm perfectly fine with you saying that there's no solution at that point. Again, the other thing is just go all the way through, and then at the end making sure that you cross off the solution that you come up with. In either way, though, I would be looking for you to identify that there is no solution to this equation. So again, the reason there's no solution, we ended up squaring a negative, so there was no way for that equation to be solved. Example 3 is a little bit different. On the right side we have an x plus 2. So it is ready for us to square both sides, though, so we can start with that. So squaring both sides. Again, the left side is pretty simple. When we square that, we just get the 4 minus x out of the square root. We do have to square an x plus 2 on the right side. Now, again, that's not our main focus right now, so I'm just going to go ahead and write that out. But you could box or FOIL that out, or if you are comfortable with the square of a binomial pattern, you could use that pattern. This turns out to be x squared plus 4x plus 4. Now, we do end up with a quadratic equation, and so we would want to get all of our terms on the same side. And notice, again, just to keep this in your head here, we just squared an x plus 2. X plus 2 can be positive or negative, so depending on what we come up with for a solution will depend on whether we have an extraneous solution or not. So we'll have to kind of just work it out and see what happens. Back to solving this one, I'm going to go ahead and subtract 4 and add x at the same time. So adding x here, subtracting 4. So we get a 0 on the left, and we end up with x squared plus 5x. And then the 4's cancel out. So kind of a special case here. We can still solve by factoring and applying the zero product property, but all we can factor is an x out of that x squared plus 5x. So now when we have a factor of an x, we get a solution of 0. We also end up with a solution of negative 5, because that would make x plus 5 equal to 0. Now if we go back to the original, we could plug these in. Again, I can tell you though that the extraneous solution would be the value that would make x plus 2 negative. Well, 0 is fine, because when you plug a 0 into x plus 2, you just get 2. Negative 5, however, if you plug that in there, you'd get negative 3. So even without necessarily going all the way back to the original and plugging it in, I can determine that that would be extraneous. So what I would be looking for on this one is that you found the two solutions that you're supposed to, 0 and negative 5, and that you determine that negative 5 is an extraneous solution, so you cross that out. So that's the kind of thing I'm looking for there. We've got a couple more equations. With number 4, we could just start by squaring both sides. So squaring that. Again, the left side just gives us that x squared minus 4x plus 9. The right side, again, squaring that, box it, FOIL it, use the square of a binomial pattern, but you get x squared minus 2x plus 1. Now in this case, the x squareds will cancel out. We would subtract an x squared from both sides of the equation, so those would both be gone. Determining then that I would probably want to add the 4x to both sides, because that'll give me a positive x, so I may as well go ahead and subtract the 1. So doing all of that, I end up with 8 equals 2x. So we get just one solution, that x equals 4. So again, we get that from dividing by 2. Now, when we squared both sides back here, I squared x minus 1. So again, I would have created an extraneous solution if I squared a negative, but my solution I came up with 4. If you plug that in here, 4 minus 1 is 3, so still positive, so the 4 should work out just fine. Looking at example 5, now big difference here is we have two square roots. So we want to isolate one of them. It does not generally make a big difference which one we isolate. Sometimes you might look at it and decide you want to do one more than another. Most cases it doesn't make a big difference. So I would probably just subtract the square root of 3x plus 4. So that will leave me with the square root of 5x plus 6 on the left, and then 2 minus the square root of 3x plus 4 on the right. At this point, again, we would square both sides, and we would be left with the 5x plus 6 on the left. Now, on the right side, that's fairly complicated to just go ahead and square that. So if we, I'll draw a box for that so we can get a better look at how that gets squared. So, let's see, I need a 2 by 2 box, which again, it is just a 2 by 2, even though it's got that kind of binomial as one of its pieces. And so that negative square root of 3x plus 4, a 2, and a negative square root of 3x plus 4. So again, we're just multiplying it by itself because it's getting squared. So those different pieces that are there, we get a 4 here, negative 2 square roots of 3x plus 4, another negative 2 square roots of 3x plus 4, and then in the bottom right, the negatives would cancel, and then the multiply square root by itself, and you just get the radicand to come out. So we just get 3x plus 4 here. A little confusing there because the 4 and the 3x plus 4 would combine, so we'd get a 3x plus 8 for that. And we'd have minus 4 times the square root of 3x plus 4. So that's going to be the right side of our equation, so I'll come back over here and put that in. 3x plus 8 minus the 4 square roots of 3x plus 4. So notice squaring that equation both sides one time there did not get rid of all of our radicals, but it did get rid of one of the two, so we're down to just one more. So we want to try to isolate this as much as possible right now. So we'll subtract the 3x, subtract the 8. And again, I'm not really worried too much about things being positive or negative. I do get a positive 2x and a minus 2, and that's going to equal negative 4, and then the square root of 3x plus 4. Now, in this case, I probably wouldn't want to divide by the entire negative 4 there. However, if I divide by, and part of the reason I wouldn't want to do that is because that would create fractions on the left side. However, if I do divide by negative 2, that will not create any fractions, and it will reduce this down as much as possible. So that negative 2 will switch the signs here, so I'd get a negative x plus a 1, and then a 2, and then a square root of 3x plus 4. At this point, again, I would square both sides to get rid of that last radical that we have. So squaring that negative x plus 1, and squaring the 2 times the square root of 3x plus 4. And if you wanted to think of the left side as 1 minus x, that would be fine as well. And again, if you need to box or FOIL that out, that works also. We do get an x squared minus 2x plus 1 when we square the left side. And on the right side, the one thing to be careful with is make sure that you square this 2. So that 2 squared gets a 4, and then we just have a 3x plus 4 that comes out of there. We need to distribute the 4 into the parentheses, and so we get x squared minus 2x plus 1 equals 12x plus 16. Alright, I know this is getting to be a long question, but we're just about there. It is quadratic, so we'd want to move everything to the same side, so I would subtract the 12x and the 16 from both sides. So that gives us our x squared minus 14x minus 15 equals 0. Might look like it's going to be difficult to factor, but again, the difference between 15 and 14 is just 1, so it really just factors as x minus 15 times x plus 1. Alright, so with those factors, looks like our solutions would be a positive 15 and a negative 1, and I say looks like because again, we did some squaring there, so we got to make sure that we didn't square a negative at any point. Again, one way to do that is to look back at your squaring steps. So I squared a negative x plus 1 right here. Looking at what I have, I've got a negative 1. That would make, well, that would make it 2, so that's fine. And a 15, well, the 15 would be a negative 15 plus a 1. So that does not look like that works at all for squaring that. Again, you could also come back to the original and just plug those in. Sometimes for these that might be a little bit easier to do than, like I said, looking at whether you squared a negative or not. So let's see. So again, I'm not going to necessarily go through how to plug those in there, but again, you'd want to check that out. And like I said, we can already tell that the 15 would be extraneous because it makes the negative x plus 1 extraneous, and the negative 1 is going to work out just fine. So again, if I could go back to the original and look at what happens when we plug a negative 1 in here. Well, we'd get the square root of 1 plus the square root of 1 equals 2, so that's pretty simple to figure out there. So. Alright, last one we'll take a look at is, again, our one problem that's going to have a greater, or an index that's greater than 2. So we're looking at a cube root problem. In this case, we're keeping it fairly simple. Notice it's a cube root equals a cube root, so we just cube both sides of the equation. We end up with z plus 5 equals 2z minus 6, because the cubing just undoes the cube roots. We end up with a pretty basic equation to solve. I would subtract a z from both sides, so we end up with 5 equals 1z, so just z minus 6. Add the 6 to both sides, and we get 11 equals z. Again, there's really no need to check this, although you could pretty quickly. On the left, we'd get the cube root of 16, and on the right, we'd also get the cube root of 16. So even without knowing what that is exactly, we can tell that they are equal to each other. So z equals 11. Again, hopefully you found this helpful. If you have any questions, feel free to let me know, and as always, again, you want to try and practice some of these on your own.